Our final quantity for describing rotational motion will be the analog of momentum. It's called angular momentum. And just as in momentum, it's not really crucial. It doesn't give you any new physics really that underlie things, but it can be a very convenient way to explain certain behaviors and phenomena or solve certain problems. So the angular momentum, first we'll define it for a collection of point objects. And this will also work for a single object that is just not rotating on its own. So the definition of angular momentum is the cross product between an object's position vector and its momentum vector. We imagine that there's some coordinate system set up. The object has a position vector r at a given instant of time and is moving in a certain direction with a momentum vector p. And the cross product between those two vectors will give the angular momentum contribution of that object to the total of the collection. If there's just one object that you're considering, then there's just one term in this sum, and you could just take r cross p for that object. So we'll restrict our discussion of this to really motion in 2 dimensions, because in 3 dimensions it's fraught with a bunch of three-dimensional vectors and all their directions. We'll consider this in a plane, so the position vector and momentum vector will all lie in the xy plane. And so there's a couple of ways that we could calculate this angular momentum based on what we know about calculating cross products. So for a set of objects where the position and momentum are known in terms of magnitude and direction, we might imagine adding up the product of r times p times the sine of the angle between them. That would be the way to calculate the cross product for each object. But this is a little bit not so useful in practice, because you have to remember, when you do a calculation this way for a cross product, you have to decide by hand whether it should be assigned a positive or negative sign, because it only gives you the magnitude of that cross product. You have to put in the positive or negative sign by hand. So we might be able to do that if we had a collection of objects and we went through each one and thought it through, but it's not a useful formula for doing further calculations with, because we don't really know. In general, this doesn't have a definite plus or minus sign. You would have to look at it for each object. So a better way to do this, which doesn't have the sign problem, is to use the rectangular formula for cross product. We would have the x coordinate times the y component of the momentum, and both of these for then the ith object. So I'll put xi p y I minus the y coordinate of the object times p x I, like so. And this technically then would give us the z component of the angular momentum vector, but it would have the correct sign, positive or negative, for how the objects were moving. So just a little bit of conceptual exposition here about what the angular momentum really represents and what it means. Say we had a collection of objects I'll draw 4. And the objects are all at different positions, and they're all having different directions of motion, so different momentum vectors. Now for each one of these objects, it's clear if you just look at this and step back, it looks like they're kind of all going around the origin in a counterclockwise direction, right? So if we took the cross product of r position vector and the p momentum vector for this object in the top right quadrant, we would get a, say, a positive x, right? A positive y, and then we would get a momentum y coordinate that was positive and a momentum x coordinate that was negative. So we'd have positive, positive here, positive, negative here with a minus sign. That would give us a positive angular momentum. So something that is a particle in the collection that's moving in a counterclockwise direction, you know, more or less counterclockwise, gives us a positive contribution to the angular momentum. So if we add up all the contributions from all the objects and get a positive angular momentum, that means that our collection of objects has a tendency to be rotating counterclockwise. If the objects are all kind of moving together in a way that would give a, so this one has LZ greater than 0. If we had the objects all moving together in some way that looks like they'd have a clockwise rotation to them, then our angular momentum there would be negative. Whoa. Okay, so we see that if there's an overall counterclockwise circulation of the objects, then we have a positive angular momentum. If there's an overall clockwise circulation, we have a negative angular momentum. Now, what if we have an object that definitely rotates clockwise or counterclockwise? A rigid body, where all of the pieces move with the same angular velocity. Recall how we determined the velocity vector of a piece of a rotating rigid object. The x component was equal to minus the angular velocity times the y coordinate, putting the origin at the center. And the y component of the velocity was equal to the angular velocity multiplied by the x coordinate relative to the center. So this produces the familiar relationship that the magnitude of the speed for a rotating object is equal to omega times the distance from the origin, r. But let's take these velocities of the bits of a rotating rigid body and see what they give us when we plug into the formula for the angular momentum. We have to sum over all of the bits. The x coordinate of that times the y component of its momentum. Well, the momentum here is just mass times velocity, so we'll have mass times the velocity omega xi. Then we've got to subtract the y coordinate times the x component of the momentum. So that's just mass times negative omega yi. Now this sum has to be carried out over all of the bits of matter in the rotating rigid body, whether it's continuous or made up of distinct pieces. But each piece has the same angular velocity. They don't all have the same mass. We have m sub I here, but they all have the same angular velocity. So that angular velocity can actually be factored out of the sum. So we have the angular velocity omega multiplied by this sum, and let's try to simplify this sum a little. We have mi in both terms. Then in the first term we have x coordinate of the ith bit squared. Then we have a negative and a negative here, so we get a plus, and then the y coordinate of the ith bit squared. Now we can recognize this sum actually, the sum over all the bits in the rigid body of the mass of each bit times its distance from the origin squared. This is nothing but the moment of inertia. And so for a rotating rigid body, we get this beautiful relationship that the angular momentum is equal to the moment of inertia multiplied by the angular velocity. It exactly mimics our definition of linear momentum as mass times velocity, but here the quantities are replaced with their angular versions once again. For an object that's moving and rotating at the same time, we get two contributions to the angular momentum. So a moving and rotating rigid object the angular momentum, z component, being correct here, will be made up of two parts. The first part treats the object as a point particle located at its center of mass, with a velocity equal to the velocity of the center of mass point. So it's just the angular momentum we would get based off of the object as a single point particle at its center of mass. The second contribution is, so this contribution is only due to the motion of the center of mass. Doesn't depend on the rotation at all. The second contribution is from the rotation of the rigid body about its center of mass. So these two parts are called the orbital contribution. So the orbital angular momentum. It's called orbital because the whole object is moving around in some trajectory or some orbit. And the second part here is with the rotation of the object itself. So this is called the intrinsic angular momentum. And that represents the kind of the rotation of the object. So stuff it just has on its own, independent of where it's going or what's nearby. It's got this intrinsic rotation to it, and that gives it some contribution to its angular momentum. So this is a little bit different than ordinary momentum or energy or something. We actually have two different types of motion here, and both of them contribute some amount to the angular momentum. Now let's look at one of the reasons why angular momentum is a useful quantity. And it comes from its relationship to torque. So relationship of angular momentum and torque, tau. We'll derive this relationship here by treating our system again as a collection of objects with arbitrary positions and velocities. So this will be the formula for the total angular momentum. And let's investigate this by taking the time derivative of the total angular momentum. So we have a product here between position and velocity, and as we've seen a couple times before, when we take a derivative of a product, we have to do a product rule, and it doesn't matter that the product is a cross product, we just have to maintain the correct order. So we'll have the first term will be the derivative of position times the second, which is velocity. The multiplication stays as a cross product. And then the second term in the product rule will be the first term times the derivative of the second. Like that. Now these derivatives that have occurred over here are all derivatives of position or velocity. So we know that those mean something more than just a derivative. They have all, the derivative of position is velocity, and the derivative of velocity is acceleration. So we can rewrite this in an identical form using the definitions of velocity and acceleration. Now when we get to this stage, we notice immediately that we have the first term here is velocity, cross product with velocity. And so those are parallel vectors, and so their cross product is 0. And then in the second term, we notice that we've got acceleration here and a mass here. So we can put the mass and acceleration together, and that will be equal to the, by Newton's second law, mass times acceleration is equal to the net force on that bit of the object. So F sub I stands for the net force due to all external and internal forces on the part of the system at location I. Now we've got left here is the cross product between position vector and force vector, and that just is our definition of torque. And we're summing up over all of the possible torques acting on the system, internal or external, and so this is the net torque. All right, so a very useful relationship that we derive from this definition of angular momentum by taking its derivatives. The total derivative of angular momentum with respect to time is equal to the net torque on the system. And this matches exactly what we saw for Newton's second law with linear momentum P and net force F, right? The net torque, if there's a net torque, what it does is it changes the angular momentum of the system over time. So we can use this to relate net torque to changes in the angular momentum. So this is technically, when we change these into deltas, this has to be the average net torque. And I've kept the vector signs in here so it shows you that when a torque acts, remember the direction of the torque points along the axis of rotation that torque would tend to rotate about. When a torque acts, it moves the angular momentum vector, it has a delta, it moves the angular momentum vector closer to the direction of the torque vector. Right, so a torque can increase or decrease the angular momentum, and it can also change its direction, similar to how a force can change the direction of momentum or increase its magnitude or decrease its magnitude. So the other conclusion that we can get from this is a conservation law. Since we've got a time derivative over here, if the net torque on the system is 0, so there may be external forces, but if none of those external forces generate any torque, then the net torque on the system would be 0, and its angular momentum would be constant. So if the torque net is 0, then angular momentum equals a constant. So we can set up conservation of angular momentum as a principle when we can argue that there's no net torque in a system, even if there are many rotating parts internally or external forces. As long as there is no net torque from the outside, then the angular momentum of the system will remain constant. Now let's do an example problem where we use conservation of angular momentum. An ice skater is rotating at 4 radians per second and has a moment of inertia of 1.5 kilogram meters squared. So she's spinning like this, pulls in her arms, and this decreases her moment of inertia to 0.7 kilogram meters squared. That decrease in moment of inertia is going to increase her angular velocity, and what is the final value? So in this situation, we've got the skater on the skates, relatively frictionless surface. So there's a good argument for the absence of any external torques. That means that we can apply conservation of angular momentum to the system. We treat the ice skater as a rigid object. So her angular momentum can be written as the product of moment of inertia and angular velocity. In the initial state, this is 1.5 kilogram meters squared for moment of inertia and 4 for the angular velocity. In the final state, the moment of inertia is 0.7, and the angular velocity is unknown, so we leave that as a variable. So this is what we have to solve then for the final angular velocity. It ends up being a very simple equation. We'll just multiply. 1.5 times 4 is 6, and divide by 0.7 is 8.57. Radians per second. So the rotation rate speeds up. So what else can we say about this? Well, it looks like her moment of inertia was cut by a little bit more than half, so her angular velocity went up by a bit more than doubling. One other thing to notice here is that in this process of changing the moment of inertia, the rotational kinetic energy of the ice skater would actually go up, because rotational kinetic energy is equal to 1/2 I omega squared. So the product of I and one factor of omega remains constant. Because there's two factors of omega here, if the angular velocity goes up, then the kinetic energy goes up as well. So the skater actually has to do some work to pull in her arms against, cause a centripetal force that pulls them in to increase this kinetic energy and do some work, right? So even though angular momentum is conserved, the total kinetic energy here is not conserved. Just pulling in her arms makes her do some work and makes her speed up. Okay. For the second example, we'll set up a wooden wheel, radius 1 meter, and a total mass of 3 kilograms. So mass of the wheel will be 3.0 kilograms, and we'll treat this wheel as a solid disc or cylinder. In the horizontal direction, a bullet fired from a gun approaches this wheel at a distance of 0.5 meters away from the center. So its velocity is totally horizontal, but it's 0.5 meter away from the center of the disc. The bullet has a mass of 20 grams and is moving initially at a speed of 200 meters per second. The bullet is going to strike this wheel, and since it's made of wood, the bullet will stick inside the wheel and they'll both come to rest. So in the final state, we will have a disc with the bullet embedded inside of them, moving at the same angular velocity. The center of the disc is fixed. So that the center of mass of the disc cannot move, it can only rotate. So some force does have to be applied at the axle to keep this thing stationary, but that force doesn't apply any torque to the wheel. So it's not going to cause any change of the angular momentum on its own. Okay, so our question then is, how fast is this wheel turning after it's hit? So this is the wheel, and the initial angular velocity of the wheel is 0, and basically what we're looking here for is the final angular velocity of the wheel. Okay, so what do we have? We've got a wheel, it's got a force at the center which doesn't cause any torque, it's got no other forces acting on it. The bullet is, just flying along. It has no other forces acting on it. There will be a force of interaction between the bullet and the wheel, and that will cause them to trade some angular momentum. But since there's no external torques on the system overall, then the total angular momentum will be constant before and after this collision. So let's set up our equation as basically conservation of angular momentum. Then we just have to think about what are the sources of angular momentum before the collision and what are the sources after the collision. So before the collision, the wheel is at rest. It's not moving, it's not rotating. So the wheel has no angular momentum beforehand. What about the bullet? The bullet is not rotating or spinning, so it has no intrinsic angular momentum. But the bullet is moving in a way that gives it some orbital angular momentum. It's moving horizontally to the right, while it is vertically displaced with a positive y coordinate. So our initial angular momentum comes from the orbital angular momentum of the bullet. We're going to give it an x velocity of 200. So we'll have 200 meters per second. A mass of 20 grams, so 0.02. 0.02 kilograms for the mass. And the x component, or the y component of the displacement is 0.5 meters. Now this is the second term in the formula for orbital angular momentum, where it was m times r cross v, which is going to reduce to it in terms of rectangular components. It's going to be x vy minus y vx. So we're only getting a contribution. What we're writing down here is basically this second term, y times vx, since vy is 0 for the bullet. So we'll have minus mass times y coordinate, minus mass times y coordinate times speed. So that will be all of our initial angular momentum. Now for the final angular momentum, we're going to have a rotating object all together. So we'll have 1/2 times the moment of inertia times the angular, no 1/2 there, just moment of inertia times angular velocity of the wheel in the final state. So the moment of inertia of the wheel is a crucial quantity here. Let's work out what that is. Now, if we're careful, we realize that the the object that's rotating after the collision is actually the wheel plus the embedded bullet. And it turns out the embedded bullet won't make much of a difference since the wheel is so much heavier, but let's include it all the same. So we have two objects rotating together on the same axis, so we can add their moment of inertias. For the solid disk, it's going to be 1/2 times its mass times its radius squared. So 1/2 mr squared for a solid disk or solid cylinder. Then we've got the bullet, which is a single point object essentially. So we'll just have mr squared. So the bullet is 20 grams, so 0.02 kilograms. And somehow then it does matter sort of how far the bullet goes into the object, right? If it sticks at the edge here, then it's going to be ending up 1 meter away from the center. If it penetrates in some distance, then it's going to be closer to the center. We will actually just kind of estimate the difference there. This number is, there's no calculation for this. This is just made up as given in the problem. The bullet penetrates until it has an R value of 0.06. That's not possible. Let's put it at 0.6 meters. All right, so the wheel is 1 meter in diameter. The distance here, the closest that it could get to the center is 0.5, so let's just call it 0.6. All right, so for that object, it's going to be mr squared, 0.6 meters squared. Okay, so what we can see from this is we got 0.6 here squared is going to be 0.36 times 0.02 this contribution is going to be really small compared to this one, which is already at, so this is 1 times 1 times 3 over 2. So this is 1.5. This one is going to be much less than 1. So what we'll write out for this moment of inertia is 1.5 approximately kilogram meters squared. Okay, so putting all this stuff together, then we've got an equation that looks like negative 200 meters per second times 0.02 kilograms times 0.5 meters equals 1.5 kilogram meters squared times the final angular velocity of the system. So when that's solved for the final angular velocity, we get minus 1.33 radians per second. Right. So this wheel ends up rotating in the negative direction, so clockwise, that makes sense, and about 1 radian per second. This ends up being about around 80 degrees per second. So kind of a lackadaisical rotation there from getting struck by this small bullet. Okay, so that's an example where we use conservation of angular momentum. We've got some angular momentum that's orbital and some that is intrinsic to two different objects. And those all get thrown in the same pot for total before and after we set up this conservation equation, and then that allows us to predict one of the unknown quantities. In this third example, we're going to use our knowledge of both conservation laws to solve the kind of problem that you always imagine physics or scientists could solve. Two cars, or a car and maybe a motorcycle, collide on the road, and there's certain parameters of their impact, and we want to know where they're going to go or how they're going to move afterwards. So the car is modeled by a rectangle with its bottom left corner at the origin, length of 2 meters and a height of 1 meter, and a total mass of 1,000 kilograms. And initially it is at rest. So we'll call that the car at rest. And this car is about to be struck by a smaller object of mass 250 grams, a length of 1 meter, a height of 0.5 meters, and it's 0.5 meters above the axis. This object is moving to the right at 20 meters per second, and what's going to happen is it's going to collide with the back top corner of this car and basically stick together. So we're looking at an inelastic collision here, where afterwards the picture would look like a single object composed of two pieces. One rectangle at the bottom, 2 meters and 1 meter in dimension, and a smaller rectangle attached to the top, 1 meter across and 0.5 meters tall. So this overall object, after the inelastic collision, will have some center of mass velocity, and it will have some rotational velocity. So we'll use both conservation laws to try to figure out what those are. First, let's look at conservation of momentum. Since there are no external forces in this case, we'll have a conservation of momentum between an initial momentum that is just due to the smaller object, so 250 kilograms, times 20 meters per second. This will be equal to the total mass of the objects when they're stuck together, which is 1,250 kilograms, multiplied by the final velocity of the objects. Now, the great thing about conservation of momentum is that this goes on independent of the ability of the objects to rotate. So the fact that they might rotate, it makes no difference to their linear momentum. If there's no external forces, this still has to be conserved. So our final velocity then is going to be basically, we're going to have 250 over 1250 is a factor of 1/5, so we'll have 20 over 5. So this final velocity is going to be 4 meters per second to the right. Now for the conservation of angular momentum, it's somewhat easy to figure out the initial angular momentum because the car is not rotating and not moving at the beginning, so the car doesn't contribute any angular momentum. The motorcycle is not rotating, but it is moving in a way that gives it some orbital angular momentum. So to get this, we have to look for the center of mass of this object and its velocity. So its velocity vector is purely in the x direction. It's positive x. So we're going to have that negative m v for the momentum in the x direction. And then the positive y coordinate of the center of mass. So it's 0.5 to the bottom of this object and another 0.5 meters to the top. So the center of mass, its vertical coordinate for the center of mass is going to be at 0.75 meters. That's the geometric center of that object. So 0.75 meters for the center of mass of that object. So let's calculate numerically then what the initial angular momentum will be. So it's negative 3,750 kilograms meters squared per second. Okay, so that's the initial angular momentum, and it makes sense to be negative. It makes sense to be negative because this has an overall clockwise direction to its motion. Okay, now after the collision, it's more difficult because we have two types of angular momentum. First of all, we have the orbital angular momentum because the center of mass of this combined object is moving. And then we have the rotational angular momentum, which we have to get by looking at the moment of inertia. So first let's look at the orbital contribution to the final angular momentum. We know that the formula for this is going to be m times the final velocity. The final velocity is all in the x direction, so we'll have a minus sign in front and then the y coordinate of the center of mass for the object. Now, how about this y coordinate for the center of mass? Well, we have two objects that we know the center of mass of each one of those. It's at their center, and so the center of mass of the combined object can be gotten by treating these as point particles. So our YCM for the combined object will be 1,000 kilograms times the center in the y direction of the car, so that's at 0.5 meters, plus 250 kilograms for the bike, and the center of the bike is up there at 0.75, the same one we used here, so 0.75 meters. And that will be divided by 1,250 kilograms for the total mass. So let's work out that. We get 0.55 meters. Okay, so that's the y coordinate of the center of mass. So this orbital contribution, we'll call it LFO. We actually can find out. The total mass of the object is 1,250. The final velocity was 4 meters per second. We knew that from conservation of momentum. And the y coordinate of the center of mass is 0.55 meters. So our orbital angular momentum after the collision is going to be 2,750. And that's also got the minus sign in front of it, right? Because we've got the x component of velocity and a y component of displacement. So that's negative 2,750 kilogram meters squared per second. Okay, so a large portion of the initial angular momentum is taken up just by the motion of the car and bike's center of mass together. But there is some left over. That's the rest that's going to come into the rotation that this collision gives the system. So it's as simple then as saying that the final angular momentum due to the intrinsic portion is going to be I omega f. And we have minus 3,750 equals minus 2,750 plus I omega f. So this is the conservation of momentum equation. Before we have all orbital, and afterwards we have some orbital and some intrinsic. Now we're going to have to do a bit of work to figure out the moment of inertia of this object, and we'll probably have to look in some tables. So let's grab those tables and find out what we get. Okay, to calculate this moment of inertia, we'll need to use the moment of inertia for a rectangular shape, and we'll need to use the parallel axis theorem because neither of these shapes are centered on the center of mass. They're displaced somewhat. So our total moment of inertia is going to come from 4 pieces. First, we'll have the moment of inertia of each rectangle about its center. And then we'll have the moment of inertia of each rectangle considered as a point some distance from the center of mass. So I went ahead and calculated the y-coordinate of the center of mass of this and the x-coordinate for the center of mass of this. It's 0.7 for xcm and 0.55 for ycm. So let's set up our formula for the total moment of inertia. For the large rectangle, we have 1/12 the mass, which is 1,000, times the sum of the length squared plus the height squared. Then we need to add in the portion from the parallel axis theorem, which is the mass times the distance from the center squared. So the center of the rectangle here is at 1 meter over in x and half a meter up in y. So we have a distance to the center we'll get from Pythagorean theorem. We're taking the distance between the coordinates 1, 0.5, and the coordinates of the center of mass. So we'll have 1 meter minus 0.7 meters for the x displacement squared, plus 0.5 meters minus 0.55 meters for the y displacement squared. So that's the contribution to the moment inertia from the large rectangle. There's 2 more terms then that are similar. This is for the intrinsic moment of inertia for the bike, 250 kilograms, and a length of 1 meter squared and a height of 0.5 meters squared. And then the contribution owing to the distance of this point at the center of the motorcycle to the center of mass. So there we'll have an x-coordinate of negative 0.5, and a y-coordinate of 0.75. So 0.75 meters minus 0.55 meters all squared. So that is our lengthy formula for the moment of inertia of this combined object. That moment of inertia comes out to 905.2 kilogram meters squared. So with that value finally figured out, then we can solve in the conservation of angular momentum equation for the final angular velocity of the system. this is going to be equal to the difference, 3750 minus 2750, is negative 1,000 on the left, and then we'll just have to divide this by that moment of inertia, 905.2. So our final angular velocity is 1.104 radians per second. All right, so then we can make our conclusion. After this collision happens, the final state of the object is one combined object with a center of mass about there. The center of mass moves to the right at a constant velocity of 4 meters per second. And while it moves to the left, the center of mass just keeps going. The object rotates about the center of mass in the negative direction with an angular velocity of negative, I forgot the negative down here, an angular velocity of negative 1.1 radians per second. Okay, so that's basically what we expect to happen in this kind of collision. You know, these things slam together, it jolts them off to the right, and then they this kind of off-center hit, so it kind of makes it start to spin. But the great thing about the conservation laws is now we can calculate or predict exactly how big those motions will be.